Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we were taking a deep dive into the very core of structural analysis, tackling the concepts that separates a simple calculation from a reliable, complex structural design. Our mission is to demystify two massive areas engineers wrestle with every day. First, we need to understand how real-world loads combine to create complex stresses. You know, we're talking about components that are being both pushed and bent at the same time. And second, we'll explore the powerful methods we use. We'll trace the evolution from classical difficult integration to the elegant shortcuts of energy principles. And finally, the numerical power of matrix algebra. All to predict if a component will deflect too much or just fail outright.
It's a perfect map for this journey.
Yeah.
We're definitely stepping beyond the easy case of, pure tension or compression. Structural success, especially when you're dealing with non-uniform loads, it all hinges on accurately modeling those combined effects. And as soon as you have those combined stresses, you absolutely must have rigorous, accurate deflection analysis. That need for efficiency is what pushed engineers toward, sophisticated tools like energy methods and the vast matrix algebra that drives every modern simulation today.
Okay, let's unpack this starting where the rubber meets the road.
Yep.
Combined stress. As you said, it's rare that a real column or a strut only feels force directly down its center. So if I have a short, stocky strut, maybe steel post, and the load is slightly off-center, what exactly happens inside that material?
What happens is a beautiful demonstration of superposition. When that component is subjected to simultaneous bending and thrust, the resultant longitudinal stress, we call it sigma, it's really just the sum of two perfectly separate stress systems.
So you're just adding two different effects together.
Exactly. You're combining two types of deformation. The first, and the simplest one, is the average compressive stress from the axial load, P. That's just P divided by A, where A is the cross-sectional area. That's your uniform squeeze.
Got it. That part's straightforward. It's evenly distributed across the whole area.
But the second part is the non-uniform stress, the one created by the bending moment, M. That stress is calculated as M multiplied by Y and then divided by I sub X.
And remind us what Y and I sub X are.
Sure. So Y is the distance from the neutral axis, and I sub X is the second moment of area, which is, it's basically the shape's inherent resistance to being bent. It's the stiffness that comes from the geometry itself.
So if we're analyzing a point, we literally just calculate the uniform squeeze, and then we add or subtract the stress caused by the bending at that exact point. Sigma equals P over A plus My over I sub X.
Exactly right. And that brings us immediately to a critical real-world scenario, eccentric thrust.
When the load is off-center.
Right. When the load P acts slightly off-center, we call that distance the eccentricity, E sub Y. It is statically and mathematically equivalent to two simultaneous effects acting right at the center. You have a simple axial thrust P plus a pure bending moment M, where M equals P multiplied by E sub Y.
Ah, okay. So this is what you'd see in, say, poorly aligned machinery or columns where the connecting beam isn't perfectly centered.
Precisely. The offset distance, no matter how small, it automatically converts part of that downward force into a side-to-side rotational moment, and that dramatically changes the stress profile.
Which leads to some very important design rules, I imagine.
It leads to a crucial one, especially in materials like masonry or concrete, which have practically no strength and tension. We have the no tension rule. When you combine that bending and thrust, tensile stresses, the pulling stresses, are going to occur in the fibers farthest from the center on the side, away from the load.
So you're squashing one side, but actually pulling the other side apart.
That's it. And for a component with a simple rectangular cross-section, if you want to ensure that no part of the material is being pulled apart, zero tensile stress, the eccentricity, E sub Y, must be limited. The load P can only act within the middle one-third of the section. The absolute limit on that eccentricity is 1/6 of H, where H is the depth of the column. If the load moves beyond that central core, that 1/6 limit, you start creating internal tension. And in concrete, that means cracking, and that means eventual failure.
That 1/6 rule is a fantastic, memorable detail. It just shows that in structural engineering, a tiny deviation in load placement can completely change the failure mechanism. Now, let's pivot from strength, whether it breaks, to stiffness, which is how much it moves. Why is deflection just as critical as strength in design?
Well, stiffness is non-negotiable. It's because structural components have to be both strong and stiff enough. A strong beam that sags too much might not collapse, but
it's still a failure.
it's a functional failure, absolutely.
Yeah.
It can crack ceilings, cause equipment misalignment, or just be unusable. The design has failed.
So mathematically, how do we capture that inherent resistance to bending?
We use the term flexural stiffness, which you'll always see as E. E is Young's modulus, the material's intrinsic stiffness, and I is that second moment of area we just talked about, the geometric stiffness.
So a stiff design has a high EI.
A very high EI. And the fundamental relationship for elastic bending links the curvature, which is 1 over r, directly to the loading, m, and the stiffness. It's 1 over r equals m divided by EI. This simple relationship, though, immediately takes us down the rabbit hole of classical calculus. It leads to the governing differential equation for deflection.
Okay, lay on us.
If v is the vertical deflection along the length z, the equation is EI, multiplied by the second derivative of v with respect to z squared equals m, the bending moment.
That equation looks simple enough on paper, but solving it in the real world. I mean, for a complex beam, maybe one with a distributed load that stops halfway or point loads all over, that requires integrating that moment equation multiple times. And dealing with those discontinuities sounds like a nightmare.
It absolutely is. When the load changes abruptly, the equation for m changes, and you have to perform multiple integrations, applying boundary conditions every single time. It turns into pages of messy work.
So how did engineers find an elegant fix for this mathematical headache?
Well, necessity is the mother of invention, right? That need to handle discontinuities efficiently led to tools like Macaulay brackets.
Ah, the square bracket.
Those specific square brackets, they simplify the whole integration process. The clever part is that the term inside the brackets only applies. It only exists mathematically when that term is positive.
So if a load starts at z equals 4 and your bracket is z minus 4, that load only counts when z is greater than 4.
You've got it. It's an elegant fix to avoid integrating piecewise functions over and over. It packages all the transition points into one unified equation.
But even that is still calculus. If we're trying to find the deflection on a massive, statically indeterminate structure, one where you can't even find the support forces with simple statics, the calculus must get overwhelmingly complex.
It does.
So what was the next great conceptual breakthrough, the shortcut to the whole deflection problem?
That's where we make the conceptual leap to energy methods. For statically indeterminate structures where you have more unknown reactions than equations of equilibrium, classical integration is almost impossible. Energy methods just bypass the entire force calculation and go straight to displacements.
Okay, tell us more about the foundation of this.
The foundation is the principle of virtual work. Simply put, for any system in equilibrium, the net work done by the forces during any arbitrary virtual displacement is zero.
A virtual displacement, so a tiny imaginary movement.
Exactly. When we apply this to beams, we equate the external work done by a unit load, a single reference force we place where we want the displacement, to the internal work stored as strain energy. The equation becomes the integral over the length L of m multiplied by 1 over rdz, which equals the work done by our unit load, let's say 1, moving through the actual displacement, delta.
So you're equating external work to internal energy. That's beautiful, but it still sounds like we have an integral to solve. Where's the powerful shortcut?
The truly powerful nugget is the concept of complementary energy, which we call C. This is the ultimate engineering shortcut for finding deflection. Instead of integrating moments, you just define the total complementary energy function for the whole structure.
Okay.
And here's the key. The magic is in differentiation, not integration. The partial derivative of that complementary energy function, C, with respect to an external load, say W sub 1, gives you the corresponding displacement, delta sub 1.
Wait, really?
Really, you plug in your total energy function, take a derivative with respect to the load you care about, and out pops the displacement at that exact location. It's a direct, elegant path to the answer.
Wow. If classical calculus is mapping a journey mile by mile, energy methods are just looking at the start and end points to find the displacement. That conceptual groundwork, I mean, it must have paved the way for modern computation.
Absolutely. The energy principles, coupled with methods like Rayleigh-Ritz, formed the critical foundation for all modern numerical analysis. They showed engineers how to turn structural behavior into a system of solvable linear equations.
Leading us directly to the numerical realm, which is necessary because when you jump from a simple column to an aircraft fuselage or an offshore oil rig, the complexity scales beyond anything manual calculation can handle.
Exactly. When the structure becomes that massive and interconnected, manual methods break down completely. We have to transition to numerical methods, and the fundamental language they speak is matrix algebra.
Okay, for listeners who might be a bit rusty on this, let's keep it grounded. In this context, what role does a matrix actually play?
A matrix is simply a structured way to store and manipulate massive amounts of data at the same time. Just think of it as a rectangular table of numbers. In structural mechanics, it lets us represent connectivity, material properties, forces, all in an organized, computable way.
So it's about organization.
It is. Knowing a matrix is, say, order 4 by 3, 4 rows and 3 columns, tells the computer exactly how much data it needs to process and how it relates.
And why are these arrays so vital? What core principle do they allow us to implement?
Matrices are the foundation of the matrix displacement method, and from that, the finite element method, or FEM. They let us represent the entire complex structure as a single, vast system of simultaneous linear equations. The system is often expressed very compactly as a relationship between 3 vectors: the force vector, P, which has all the external loads, the stiffness matrix, K, which holds all the properties in geometry.
The DNA of the structure, you could say.
That's a great way to put it. And the displacement vector, U, which contains all the unknown deflections. The relationship is simple. P equals K times U.
So if we can solve for those unknown displacements, you know exactly how the structure is behaving under load P. And the finite element method, FEM, that's the ultimate manifestation of this matrix approach, isn't it?
It is. FEM takes that initial complex structure and, using that matrix framework, subdivides it into thousands or millions of simpler finite elements, like little triangles or bricks. The behavior of each small element is calculated with matrix algebra, and then all those individual stiffness matrices are compiled into a massive global stiffness matrix, K. By solving P equals K times U for the whole system, we get the nodal displacements and all the resulting stresses everywhere.
It lets us simulate the complex deformation of an entire suspension bridge or the wing of an airplane.
That's right.
That is an incredible evolution. We began with combining simple axial stress with bending stress to handle eccentric thrust, a problem solved with a formula and a simple rule like the 1/6 limit. Then we wrestled with the painful calculus for classical deflection before gratefully accepting the elegant shortcut of energy and virtual work methods. And finally, we see how that groundwork leads directly to the powerful numerical framework of matrix algebra and FEM, letting us tackle any structural complexity imaginable with a computer.
And the utility of mastering these concepts is profound. Whether you're calculating the strength of a component by hand or simulating a structure on a supercomputer, the theory anchors the safety factors. For instance, the source material emphasizes the load factor. The amount loads can be increased before total collapse. Understanding those theoretical limits, which are based on these core stress and stiffness concepts, is
Yeah.
it's paramount to ensuring a safe design.
That theoretical grounding is everything. So, building on our earlier discussion, we learned that in composite bars like steel and concrete, stress adjusts based on the Young's moduli, the E values, to ensure they stretch equally. But here's something to think about. If you design a steel-reinforced concrete beam where the materials have vastly different elastic properties, what unexpected internal stresses arise before any external load is even applied simply due to construction or temperature changes? That's something for you to mull over as you consider how those initial internal forces dictate a structure's final capacity. Thank you for joining us for this deep dive into the world of mechanical analysis.
Always a pleasure exploring the structural scaffolding of the world.